Welcome. Today we're going to talk about electron configurations in the periodic table. In our last video, we talked about quantum numbers. And just to review, there are four quantum numbers. Every electron in an atom has its own set of four quantum numbers. In other words, no two electrons can have the same four quantum numbers. There's n, the principal quantum number. There's L, the angular momentum quantum number, which is a sublevel. When L is 0, we're talking about the S sublevel. When L is 1, we're talking about the P sublevel. When L is 2, we're talking about the D sublevel. And when L is 3, we're talking about the F sublevel. Then you have the magnetic quantum number, which is any integer from negative L to positive L. So when L is 0, there's only one magnetic quantum number, 0, and that means there's only one S orbital. And in any principal quantum number, in any energy level, you only have one S sublevel, which contains one S orbital. Notice that in the first quantum number, you don't have any P's. In that first energy level, that first principal quantum number, you don't have any P's because L can only be 0. But when L is 1, starting at the second energy level, or the second quantum number, when n is 2, L can be 1. And L being 1 is the P sublevel. And when L is 1, M sub L can be negative 1, 0, 1, which tells us there are 3 P orbitals in the P sublevel. That means that starting at the second energy level, the second principal quantum number, you can have 3 P orbitals, each holding 2 electrons of opposite spin for a total of 6 electrons that fit in the P orbital. When we get to the third quantum number, we have 0, 1, and 2 sublevels, any integer up to n minus 1. So when L is 2, that represents a d orbital. And when L is 2, M sub L is negative L to positive L, any integer from negative L to positive L. So we've got negative 2, negative 1, 0, 1, 2, or a total of 5 d orbitals. So the d sublevel contains 5 orbitals. Each of those orbitals can hold 2 electrons of opposite spin for a total of 10 electrons that fit in the d orbital. And then finally, starting on the fourth energy level, we can have an angular momentum quantum number of 3, which represents the F sublevel. When L is 3, M sub L can be any integer between negative L and positive L. So that's 1, 2, 3, 4, 5, 6, 7 integers, for a total of 7 F orbitals within the F sublevel. Each of those F orbitals can contain 2 electrons of opposite spin, so there are 14 electrons that can fit into the F orbital. And notice that the F orbital doesn't start until the fourth energy level. So let's go to the periodic table. I'm going to zoom in here a lot so we can write what we're doing. So we don't really need the identity of these elements. You can find them elsewhere, but the first one is hydrogen. That first electron, so let me just say that electrons fill atoms from lowest energy to highest energy. So they always choose that lowest energy configuration. So here would be 1s1, and all the way over here would be 1s2. These are all the electrons in the 1 energy level, right? So that's the first row of the periodic table. There are only 2 electrons that fit in the 1s level. Remember, we've got that equation, number of electrons in any level is equal to 2n squared. In this case, for the first energy level, when n equals 1, 2 times 1 squared is equal to 2. Now we go to the second energy level, 2. The electrons still fill up the lowest energy first, and s orbitals are lower energy. So this is going to be 2s1, and this is 2s2. Once the s's fill up, remember that the p's start in the second energy level. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. That's the second energy level. In the third energy level, we have S's, P's, and remember, this is where the D's make an appearance. But still, they fill the low energy first. So we do the 3s1, 3s2. 3p's are lower energy than the D's. And then you would think the 3Ds go here, but they actually don't. Okay, so this is where it gets a little confusing. We can admit that we have that this is the fourth energy level. It's the fourth row of the periodic table. By the way, just to catch up, when n equals 2, 2 squared is 4 times 2, only 8 electrons fit. So that was 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. In the third energy level, when n equals 3, 3 squared is 9 times 2 is 18. Okay, so the first 8 electrons are in the p's. So this is what gets a little funky, okay? And this is about energy. Again, electrons will fill the lowest energy first. And so electrons in the fourth energy level actually fill the 4s first. Because if you look at an energy diagram, and I haven't printed one out, so I'm gonna make a really crude sketch here. If we're looking at increased energy, the lowest energy is going to be your 1s. And then your 2s is going to be a little bit higher energy. And then your 2p's are a little bit higher energy than that, right? And then, of course, your 3s is going to be higher energy than the 2p. Your 3p's are going to be slightly higher energy than the 3s's. And then, of course, we have the 3Ds, but notice this. Here's the 4s. And we'll put the 4p's up here just to be consistent. The 3Ds are actually a little bit higher energy than the 4s's. So I'm going to make 5 of them because there are 5 d orbitals. So actually the 3Ds are out here. So in order of filling, it fills lower energy first, right? 1s, 2s, 2p, 3s, 3p. And instead of going to 3D, 4s is a little bit lower energy than 3D. And so it goes 3D and then 4p. So how does that look here? This section here are these 3D orbitals. They fill behind. So the periodic table actually lists them in order of filling. So they fill behind the 4s's. And notice there are 10 of them. And then what fills after the 3Ds? Well, the 4Ps. So we go back to 4, and we have 4P1, 4P2, 4P3. You get the picture. Let's go to 5. Remember, it's the fifth energy level where the s make an appearance, right? Well, we know that these are the lowest energy is going to be 5s. Actually, I said that wrong. Let me rephrase that. It's the fourth energy level where the f's make an appearance, but we don't have the f's yet because the f's are higher energy than the 5s's. It's higher energy than the 5p's, and of course, it's higher energy than the 4d's. So it's going to fill up in this order. We've got the 5s's. Here again are the 4d's. They're one row behind. Notice. And then we'd be back to the 5p's. And then, again, we still haven't filled the 4f's, but guess what? 6s1 and 6s2 are actually lower energy than the 4f's. And where are the 4f's? Well, they're actually down here. They would fit here, if you notice in a periodic table, I don't think I have one printed out right here, but if you notice a periodic table, if you follow the atomic numbers, here I'm at periodic table, ptable.com. So we are at 6, right? 55, 56. And notice this gap, 57 through 71, because this is 72. They're just put down here. There are periodic tables that are that squeeze these lanthanized actinides in here. These are the intertransition metals. If I find one, I'll show it to you. But that is actually where the Fs appear. And remember, the Fs actually started appearing in the 4th energy level. So here would be the 4F1, 4F2, 4F3, 4F4, 4F5, 4F6, 4F7, 4F8, 4F9, 4F10, 4F11, 4F12, 4F13, and 4F14. Actually, generally, I'm gonna do a little edit here. So these periodic tables I actually don't prefer. I like having 14 here for obvious reasons. There are 14 F orbitals, but sometimes what they do, I hope I didn't delete the whole page. Okay. Sometimes what they do is they stick the 3, I don't know how to do that. Okay. They stick the 3D right here. So this would be, not the 3D, the 5D, sorry. 5D is next. They'll put the 5D one, and then they would start the Fs here. I don't prefer this because it sort of disproves my point, but my point is the same. But to me, if I were working at periodic table factories, which I don't do, I guess I can print my own. There are some that do this. There should really only be 14 columns because there are 14 electrons that fit in this. There are 14 electrons that fit in the F sublevel because there are 7 F orbitals. Okay, so you go through that. Once the 4Fs fill, then the 5Ds fill. This is the order of filling. That's how the periodic table works. And then once the 5s are filled, we're back at the 6P, 6P2, 6P3, 6P4, 6P5, and 6P6. Okay, and then all periodic tables up to this point only go up to the 7th row. That's 118 elements. Oops. 7S1, 7S2. Remember, we go back to, well, we'll call this the 61. I don't know why they do this, but, and then we go to 5F1, 5F2, 5F3, 5F4. And then from the 5Fs, we go to the 6Ds. And then we go to the 7Ps. Oops, that was a really bad P. Okay, so from the periodic table, you can actually figure out the electron configuration of any atom. So for example, if I go back and let me find an atom. Let's say I like silver. So let me highlight silver. I think this is silver here. Okay. If I wanted to do the electron configuration of silver, well, I know it ends in 4d9, but it has to include everything up to that point. So it has to include, starting with the first row, the 1s2. Oops. The 1s2. It has to include the second row, the 2s2 to the 2p6. In other words, we're working our way up to here. So we got 2s2, 2p6. Now we're on the third row. We have to include the 3s and the 3p. Now we're in the fourth row, because notice silver is in the fifth row, right? So the fourth row, we've got 4s1, 4s2. We have the 3ds all the way through 10. Then we have the 4p's, 4p6. Then we have the 5s2. And then we're about where we need to be. We're here, and we need to go here. So the last part is 4d9. So that would be the electron configuration of silver. You can do that straight from the periodic table. However, what I find is it's much easier to do on a shorthand electron configuration or a noble gas configuration, noble gas notation. And that is, so these are the noble gases here. So you can start from the previous noble gas. You can't start from anything other than in this table. So the previous noble gas is here. That previous noble gas is, I guess that's krypton, right? You'd find that on the periodic table. So I could do, and I have to put it in brackets, okay? Krypton. And when I put in brackets, that means all the electron configuration up to and including krypton. And then I just start from where krypton leaves off. So here's krypton. So I just do the S's and the D's. So I just do, what is it, 5s2 and 4d9. And so that is the shorthand electron configuration. So that's obviously a lot easier to do. And so but you need the periodic table to do that. Because what krypton does, let me just highlight this in pink as well. Krypton covers the electron configuration all the way up to 4p6. So all of this up to 4p6 is the electron configuration of krypton. And then we just add onto that the electron configuration from that point up, all the way up to silver. So that's how you do it in electron configuration, and a shorthand electron configuration using the periodic table. But I also want you to notice something that's really important here, and I'm going to put this in red. Notice that in this first column, all the electron configurations end with S1. So we call that the S1 column. In the second column, they all end in S2. So we'll call that the S2 column. Notice that these here are the Ds, right? I could label each one, but I'm not going to. And these here are the Ps, right? P1, P2, P3, P4, P5, and P6. And then down here, of course, are the Fs, right? And this is 4F, and this is 5F. Okay? So there's one thing I wanted to add to this. The one thing I want you to notice here, well, I've wanted you to notice a lot of things, so bear with me, is that everything in the P6 column is the same except for helium. This is helium here, right? The reason helium doesn't end with P6, but is in this column, is that, remember, in that first energy level, only 2 electrons fit, and there's only the S sublevel. So that's why helium is 1s2. The reason it's written in this column is because when helium has those 2 electrons in the S orbital, in the S sublevel, that first energy level is full. So helium is unreactive because it already has a full outer shell. And the reason atoms react is to get a full outer shell, to be like a noble gas. So helium has the same properties of the other noble gases because it has a full outer shell. But remember that the P sublevel doesn't start to the second energy level. So that's always a trick question I include in tests, is the electron configuration of helium, knowing that it's not, you can't just figure that out straight from the periodic table because it is the exception there. So I hope this was helpful. In the next video, I'm going to talk about how to use this to figure out valence electrons.